Hello, in this lecture we will find the size of line segment AE. In the drawing we have square ABCD. We know that the size of AB is 2 units and the size of line segment DE is 8 units, and we want to find out the size of line segment AE. The size of this line segment AE so first of all we will make a construction. We'll join points D and B by a straight line. And also we know that angle DEB equals to 90 degrees. It is a right angle, and therefore triangle DEB is a right triangle. Triangle DEB is a right triangle. So we know that triangle DEB is a right triangle, therefore we can implement the Pythagoras theorem in the right triangle, triangle DEB. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. And the hypotenuse is actually side DB of the right triangle. So DB squared, the square of the hypotenuse, equals to the sum of the squares of the perpendicular, equals to EB squared plus DE squared. So according to the Pythagoras theorem, in the right triangle, triangle DEB, DB squared equals to BE squared plus DE squared. So DB squared equals to EB squared. EB equals to 2, so 2 squared is 4 plus DE squared. DE equals to 8, and 8 squared is 64. So in total we got that DB squared equals to 64 plus 4, that is 68. So I will write it down. So we found out that DB squared equals to 68. Here we will take a root out of equation number 1, and we will get that DB equals to the root of 68. So we actually found out that the size of DB, that is actually also diagonal of square ABCD, equals to the root of 68 units. So I write it down that it equals to the root of 68 units. And we also know that all the angles of a square are right angles, therefore angle DCB, this angle is a right angle. And and because of the fact that angle DCB is a right angle, then triangle DCB is a right triangle, okay? So we focus on triangle, the right triangle DCB. On the right triangle DCB, according to actually, before that, I will present to you rule number 1. According to rule number 1, the diagonals of a square, cross the angles of the square into 45 degrees angles. So read again rule number 1. Rule number 1 states that the diagonals of a square cross the angles of the square into 45 degrees. So actually we have square ABCD and we have diagonal DB, and according to rule number 1, the diagonal DB crosses the angles of the square into angles of 45 degrees, therefore angle BDC will be equal to 45 degrees, and also angle CBD or DBC will be also equal to 45 degrees. Actually, the rule means that the diagonals of a square divides the angles of the square into 2 equal parts, and because of the fact that all the angles of a square are equal to 90 degrees, the diagonals cross them into 2 equal angles, 45 degrees. This angle is 45 degrees, and this angle will be also equal to 45 degrees. Okay? So now we will focus on the right triangle DCB. On the right triangle DCB, so on this right triangle DCB, cosine is 45 degrees, equals to DC over DB. I will repeat again. In the right triangle DCB, cosinus 45 degrees equals to DC over DB. Okay? So we will define DC as y, that is to say DC equals to y, and therefore DC is y over dB is the square root of 68. So we actually found out that cosinus 45 degrees equals to y over square root of 68. We know that cosinus 45 degrees equals to root 2 over 2. So we write it down. This will be equation number 2, and according to equation number 2, root 2 over 2, square root 2 over 2 equals to y over the root of 60, square root of 68. So here we'll multiply equation number 2 by square root of 68, and we'll get that square root of 2 times square root of 68 over 2 equals to y. We know that 68 is 34 times 2, and so I write it down. According to equation number 2, y equals to square root of 2 times 68 is 2 times 34, all divided by 2. So I actually found out that y equals to square root of 2 times the square root of 2 times 34 over 2. So here we can split the root into two roots, and root of 2 times 34 equals to root 2 times root 34. So I'll write it down. We will get that y equals to the square root of 2, and we split this root into two roots, so it will be square root of 2 times square root of 34 over 2. Okay, so here we know that square root of 2 times square root of 2 is 2, so I write it down. We will get that y equals to square root of 2 times square root of 2 is 2 times square root of 34 over 2. So here 2 over 2 is 1, so 2 will get cancelled, and we found out actually that y equals to square root of 34, and actually units, and actually all the sides of square ABCD equal to square root of 34. Okay, so we can write here that DC, that is y, equals to square root of 34. BC, I'll repeat again, all the sides of a square are equal to each other, therefore all the sides of square ABCD will be equal to square root of 34. AB also will be equal to square root of 34, and AD will be also equal to square root of 34. Okay, so as you can see from the drawing, we have all the values of all the sides and all the line segments in this drawing. The only missing variable, the only line segment that are not known is line segment AE that we are looking for. Okay, so here we also know that this is a right angle, angle DAB is a right angle because it is one out of 4 angles of square ABCD, and we know that all the 4 angles of square ABCD are right angles, they are equal to 90 degrees. Now I will present to you rule number 2. According to rule number 2, if line segment AB, if a line segment AB subtends 2 equal angles, then the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So I will read rule number 2 again. Rule number 2 states that if a line segment AB subtends 2 equal angles, then the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So what is the meaning of rule number 2? The meaning of rule number 2 is that if you have this circle, and actually before the circle we have line segment AB, and the line segment AB subtends 2 equal angles, again this line segment AB subtends 2 equal angles. So we have the first angle this will be point D, this angle is theta, equals to theta. As you can see, angle theta is on line segment AB, or it lies on line segment AB, it rests on line segment AB. And we also have a second angle that also rests on line segment AB, and this angle also equals to theta in its size. So this point is point C, and this angle also equals to theta, and this angle also rests on line segment AB, or in other words, those two equal angles subtend on the same segment line AB. So if this is the reality, that we have two equal angles that subtend on the same line segment AB, then according to rule number 2, the quadrilateral ABCD, this quadrilateral ABCD is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle, and they are indeed those points are indeed lie on the blue circle. Okay, so if we have two equal angles that rest on the same line segment AB, then the quadrilateral ABCD is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. So this is actually according to rule number 2. And we can actually implement rule number 2 in our drawing. We have actually angle DAB. This angle rests on BD, on a segment BD, and then this angle DEB also rests on the same line segment BD. I'll write it down. Angle DAB rests or subtends on line segment DB, subtends on line segment DB, and it is actually equals to 90 degrees. This angle is a right angle. It is 1 out of 4 angles of square ABCD, and all the angles inside the square are right angles. And we also know it is given us in the question that angle DEB equals to 90 degrees. So angle DEB is equals to 90 degrees, also subtend on line segment DB. So I'll repeat again. Angle DEB that equals to 90 degrees according to what is given as the question, also subtend on the same segment line DB. Therefore, according to rule number 2, the quadrilateral AEBD, this quadrilateral, I will paint it in the green color in order to make it clear. This quadrilateral AEBD BD is inscribed by a circle, and those 4 points, point A, point E, point B, and point D, lie on that circle. Okay, so I will draw the quadrilateral AEBD inside a circle. So actually, quadrilateral AEDB is inscribed by a circle. So we have quadrilateral AEBD that is inscribed by a circle. So according to rule number 2, quadrilateral AEBD is inscribed by this blue circle, and the 4 points AEBD lie on this blue circle. That is actually the implementation of rule number 2 in our drawing. Okay, write it here. This is implementation of rule number 2 in our drawing. And I repeat again, the reason that quadrilateral AEBD is inscribed by a circle is because of the fact we have two equal angles, angle EAD, it is a right angle, and it subtends on line segment BD, and angle AEB, also it is a right angle that also subtends on the same segment line BD. So because of the fact that we have two equal angles that subtend on the same segment line BD, therefore according to rule number 2, the quadrilateral AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, this is according to rule number 2. And I will also present to you rule number 3. According to rule number 3, if quadrilateral ABCD is inscribed by a circle, if quadrilateral ABCD is inscribed by a circle. Then the product of its diagonals equals to the sum of the products of its opposite sides. Okay, so I read rule number 3 again. According to rule number 3, if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. Okay, if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So, what is the meaning of rule number 3? The meaning of rule number 3 is that if you have this circle and inside this circle blocks a quadrilateral ABCD, or quadrilateral ABCD is inscribed by this blue circle. So after we have quadrilateral ABCD, it is inscribed by this blue circle. So this is quadrilateral ABCD. It is inscribed by this blue circle, and we also know that side AB of quadrilateral ABCD equals to A units in its size, side BC of quadrilateral ABCD equals to B units in its size, and side CD of quadrilateral ABCD equals to C units in its size, and side AD of quadrilateral ABCD equals to D units in its size. And we also quadrilateral ABCD has two diagonals. The first diagonal is diagonal TB, and the size of diagonal BD or DB is X units, and we also have the second diagonal AC, and diagonal AC or CA equals to Y units in its size. Then, according to rule number 3, the product of quadrilateral ABCD diagonals is X times Y, and it equals to the sum of the products of its opposite sides. Actually, the quadrilateral ABCD has two opposite sides. side AD is opposite to side BC. This is the first pair of opposite sides, and we also have the second pair of opposite sides. Side AB is opposite to side DC. So the first product of the opposite sides is actually B times D, and the second product of the opposite sides, it is actually A times C. And according to rule number 3, the sum of the products of its opposite sides, that is to say BD plus AC, equals to the products of its diagonals, equals to x times y, or the products of its diagonals, that is to say x times y, equals to the sum of the products of its opposite sides. And the sum of the products of its opposite sides, it is actually BD plus AC. Okay? So we can actually implement rule number 3 in our drawing. Here we have in our drawing a quadrilateral AEBD is inscribed by this blue circle, and so because of the fact that quadrilateral AEBD is inscribed by this blue circle, we can implement rule number 3, because rule number 3 is valid for any quadrilateral that is inscribed by a circle like this quadrilateral AEBD that is inscribed by this blue circle. And according to rule number 3, whenever we have a quadrilateral that is inscribed by a circle, then the product of its diagonals, that is to say AB, we have diagonal AB, and we have also diagonal ED. Okay, so those are the two diagonals of quadrilateral AEBD, and according to rule number 3, the product of its diagonals, that is to say AB times DE, AB times DE, that is the product of its diagonals, equals to the sum of the products of its opposite sides. I will repeat again, quadrilateral AEBD has two opposite sides. Side AE is opposite to side BD, and side AD is opposite to side EB. So the first product of the opposite sides, it is actually AE times DB. And the second product of its opposite sides, it is actually AD times EB. AD times EB. So this formula, or this equation, is the implementation of rule number 3 in our drawing, because actually the product of these quadrilateral diagonals is AB times DE, and it equals to the sum of the products of its opposite sides. And the sum of the products of its opposite sides is the first product of its opposite sides is AE times DB, AE times DB, and the second product of its opposite sides is AD times EB. And the sum of the products of its opposite sides is AE times DB plus AD times EB, and it is equal to the product of his diagonals, that is actually AB times DE. Okay, so now actually we know all the variables inside this equality, so we will put the data inside this equality, and we will get that what is AB? AB equals to square root of 34 AB times DE. What is DE? DE equals to square root of 68, according to what we have already found. No, DE, actually this is DE equals to 8 units. It is given us in the question, so it is times 8 units. And it equals to AE times DB. What is AE is the variable that we are looking for, so we will leave it as it is. AE times DB. What is the size of DB? The size of DB is square root of 68, according to what we have already found, according to Pythagoras theorem. DB equals to square root of 68. So we got this equality, and we must add also the second product of its opposite sides, that is actually AD times EB. AD equals to the square root of 34, and EB equals to 2 according to what is given us the question. So we actually put the data inside this equality. We know all the variables inside this equality, and the only variable that is missing is AE. That is the variable that we are looking for, and we actually got this equality. So we know that 68 is 34 times 2, and so 34 times 2, we can split the root of 34 times 2 to 2 roots. Root 34 times root 2. So we'll do it now. We have square root of 34 times 8 equals to AE. Again, 68 is 34 times 2, and the root of 34 times 2 is the root of 34 times root 2. So we are down that it is the root of 34 times root 2 plus the root of 34 times 2. So here we can divide equation number 1 by square root of 34. So square root of 34 will get cancelled in equation number 1. And what is left after we cancel square root of 34? What is left is actually 8 equals to AE root 2 times AE. AE is the missing variable that we are looking for, plus 2. So here we will subtract from equation number 1 2, and we will get that 8 minus 2 is 6. 6 equals to the root of 2 times AE. So here we will divide the equation number 1 by root 2, and we will get that AE equals to 6 over root 2. AE equals to 6 over root 2 units. We know that 6 is 3 times 2, so I will write it down. AE, line segment AE equals to 3 times 2 over root 2. So here we will multiply this side of equation number 1 by root 2, and then we will divide it by root 2, and we will get that AE equals to 3 times 2 over root 2. So we multiply it by root 2, and then we will divide it by root 2, so we change nothing. Therefore it is allowable. So here we get that according to equation number 1, AE equals to 3 times 2 times root 2 over root 2 times root 2 is 2. So in total we got that AE equals to 3 times 2 times root 2 over 2. 2 over 2 is 1, so 2 will get cancelled. And we found out that line segment AE, that is the variable that we are looking for, equals to 3 times square root of 2 units, or in terms of numbers, AE equals to 3 times root 2. 3 times root 2 is 4.243. 4.243 units. So we actually found out the answer to the question is that this line segment AE equals to either to 3 times square root of 2 units, or in terms of numbers, line segment AE, this line segment, equals to 4.243 units. Okay, that is the answer to the question. So now I will summarize the lecture. Actually, we wanted to find out the value of AE, or the size of line segment AE, and we know that we have a square, and we know that EB equals to 2 units and line segment DE equals to 8 units, and we want to find out the size of line segment AE. Okay? So first of all, we made the construction. We joined points P and D together by a straight line, and we know that angle DEB is a right angle, therefore triangle DEB, this triangle, is a right angle. Therefore, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, dB square equals to EB square plus DE square. I repeat again, if you focus on the right triangle DEB, according to the Pythagoras theorem, dB square equals to EB square plus DE square. So dB square equals to EB square, EB equals to 2, EB square is 2 squared, 2 squared is 4, DE equals to 8 units, and DE square is 8 square, 8 square is 64. So dB square equals to 4 plus 64 is 68, or dB square equals to 68. We took a root of equation number 1 and we got that dB equals to square root of 68. So this 9/7 of the diagonal of square ABCD, dB equals to square root of 68. Then we know that all the angles inside a square are right angles, and especially this angle is a right angle, it equals to 90 degrees. So actually triangle DBC, this triangle is a right triangle. And first of all, I presented to you rule number 1. And according to rule number 1, the diagonals of a square cross the angles of the square into 45 degrees. Okay? The diagonals of a square cross the angles of the square into 45 degrees. So here we have diagonal DB of square ABCD, and according to rule number 1, this diagonal DB cross the angles, this angle and this angle, into angles of 45 degrees. That is to say, this angle will be equal to 45 degrees, and this angle will be also equal to 45 degrees. So if you focus on the right triangle DBC, we know that cosinus 45 degrees will be equal to DC over DB. Okay, cosinus 45 degrees equals to DC over DB, but we defined DC as Y, therefore DC equals to Y, so cosinus 45 degrees equals to Y, and DB equals to square root of 68. So in total, cosinus 45 degrees equals to Y over square root of 68. And we also know that cosinus 45 degrees equals to root 2 over 2. And it equals to Y over square root of 68. Here we multiply the equation number 2 by square root of 68, and we got that Y equals to square root of 2 times square root of 68 over 2. Okay? And we also know that 68 is 34 times 2. So we wrote down that instead of 68, we wrote down that Y equals to square root of 2 times square root of 2 times 34, that is actually 68 over 2. Then we split this root into 2 roots. The root of 2 times 34 equals to square root of 2 times square root of 34. And so here we have square root of 2 times square root of 2 is 2. Okay? So square root of 2 times square root of 2 is 2. And here we have 2 over 2 is 1, so 2 get cancelled. And we got that Y equals to square root of 34. So all the sides of square ABCD are equal to square root of 34. Okay? So we actually know all the variables inside all the line segments of this drawing. The only missing variable is the only missing line segment is AE, is the line segment that we are looking for. I presented to you rule number 2. According to rule number 2, if a line segment AB subtends two equal angles, then the quadrilateral ABCD is inscribed by a circle, and the points A, B, C, and D lie on that circle. So actually, if we have line segment AB that is that subtends two equal angles, then the quadrilateral ABCD is inscribed by a circle, and the points A, B, C, and D lie on that circle. Okay, so actually here we have line segment AB so I will draw it again. We have line segment AB So here we have line segment AB. This line segment AB subtends two equal angles. The first angle is angle theta. And the second angle that line segment AB subtends, it is also angle theta. So we have two equal angles that subtend on the same line segment AB. Those two equal angles subtend on the same line segment AB. Therefore, according to rule number 2, the quadrilateral ABCD, this quadrilateral ABCD is inscribed by this red circle, and the 4 points A, B, C, and D lie on this red circle. Okay, this is true according to rule number 2. And so whenever we have two equal angles that subtend on the same line segment, then we can create actually quadrilateral ABCD. In this example is inscribed by a circle, and the 4 points A, B, C, and D lie on this circle. Okay, that is actually rule number 2, and we implemented rule number 2 in our drawing, because in our drawing we have two right angles. Those two right angles subtend on the same line segment DB. Therefore, according to rule number 2, the quadrilateral AEBD is inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. Okay, so according to rule number 2, because of the fact that those two right angles subtend on the same line segment BD. Therefore, according to rule number 2, the quadrilateral AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. That is the implementation of rule number 2 in our drawing. And we also have rule number 3. According to rule number 3, if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. I read again. If quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So what is the meaning of rule number 3? The meaning of rule number 3 is that if we have this quadrilateral in the red color, quadrilateral ABCD is inscribed by this blue circle. Okay, so if this is the reality, that we have quadrilateral ABCD, that it is inscribed by this blue circle, then the product of its diagonals, the product of quadrilateral ABCD diagonals, it is actually x times y, because diagonal quadrilateral ABCD has two diagonals. Diagonal AC, the size of diagonal AC is y, and the size diagonal BD is x, and the product of its diagonals, it is actually x times y, and this product of its diagonals equals to the sum of the squares of its opposite sides. So quadrilateral ABCD has two pairs of opposite sides. Side AD is opposite to side BD, and the size of AD is D units, and the size of BC is B units. So the product of its first opposite sides, of its first pair of opposite sides, it is actually B times D, and the product of its second opposite sides, it is actually A times C. And according to rule number 3, the sum of the products of its opposite sides, that is to say BD plus AC, equals to the products of its diagonals, that is actually x times y. So whenever you have a circle, a diagonal ABCD that is inscribed by a circle, then the product of its diagonals, that is x times y, will be equal to the sum of the products of its opposite sides. That is to say, to BD plus AC, or xy will be equal to BD plus AC. And we actually also implemented rule number 3 in our drawing, because we got this drawing according to rule number 2, because of the fact that we have two equal angles that subtend on the same segment line BD. Then according to rule number 2, the quadrilateral AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. This is according to rule number 2, and according to rule number 3, because of the fact that we have quadrilateral AEBD that is inscribed by this blue circle, then according to rule number 3, the product of its diagonals, that is to say AB times DE, AB times DE, equals to the sum of the products of its opposite sides. And the sum of the products of its opposite sides is actually AE times DB. This is the first product of its opposite sides, and the second product of its opposite sides, it is actually AD times EB. And the sum of the product of its opposite sides is AE times DB plus AD times EB. And that sum of the product of its opposite sides equals to the product of its diagonals, that is actually DE times AB. Okay, so the product of its diagonals, that is AB times DE, equals to the sum of the products of its opposite sides, that is actually AE times DB plus AD times AB. This is the implementation of rule number 3 in our drawing. Okay, so here we have in this equality we have all the variables, all the variables, all the variables except of AE. AE is the only missing variable, because we know that AB equals to square root of 34, DE equals to 8 units, AE is the missing variable, DB equals to square root of 68, AD equals to square root of 34, and EB equals to 2. Okay? And the only missing variable here is AE. So we know that square root of 68, it is actually square root of 34 times square root of 2. Okay, so we substitute that square root of 68 by square root of 34 times square root of 2. Here we divided equation number 1 by square root of 34. So square root of 34 get cancelled in this equation number 1, and we got that 8 equals to square root of 2 times AE plus 2. Here we subtracted 2 from equation number 1. 8 minus 2 is 6, and 6 equals to square root of 2 times AE. Okay, here we divided equation number 1 by square root of 2, and we got that AE equals to 6 over square root of 2. Okay, we know that 6 equals to 3 times 2, so we got this equality. And then we multiplied this equality, equation number 1, by this side by square root of 2, and then we divided it by square root of 2, so we changed nothing. Okay, we got this expression. So here we know that square root of 2 times square root of 2 is 2. So in the denominator we have 2, and we got this equality that AE equals to 3 times 2 times square root of 2 over 2. 2 over 2 is 1, so 2 will get cancelled, and we left only with the line segment AE equals to 3 times root 2 units, or in terms of numbers, line segment AE equals to 4.243 units. I will repeat again. This line segment AE equals to either 3 times root 2 units, or in terms of numbers, this line segment AE equals to 4.243 units. Okay? Thank you very much.